I hope my screen is visible with the distillation column in PPT mode. Please confirm.
Yes, ma'am, it is.
Okay, thank you. So, good morning to all. In the last class, we have discussed the evaporators, and we have seen the design part of that, which includes estimation of steam consumption and the heat transfer area to uh, achieve that evaporation. Okay, so how much concentration we need, uh, how much like concentration we uh, consider from feed to product, that to achieve that, how much area and how much steam is required, that we have seen, considering a specific approach that is based on Badger McCabe method. Okay, now that you can also solve those equations simultaneously, because um, uh, we have four equations and four unknown. Okay, but the difficulty is that why we have considered Badger McCabe method. um, like when you consider those equations are non-linear in nature. Those are not linear in nature. Some of them are linear, but some of them are non-linear. And in a complete set, if any equation you find as non-linear, the whole set of equation you need to consider, you need to solve considering non-linearity. Okay, so Badger McCabe is one method. Another method is Newton Raphson method, where you convert all equations into linear form, and then we solve all linear equations simultaneously using Gaussian elimination method. Okay, so all these are the part of the numerical methods, which probably you have read in any of your course in chemical engineering, or probably in modeling course, mathematical modeling course, which is being which is also going on. So the point is, we have used a specific method with certain assumptions, and those assumptions we relax after the that after the like iteration completes. Okay, so the same thing we used to do with the Newton Raphson method also, and that was all about the design of evaporators. And we have seen a triple effect evaporator, multiple effect, more evaporator than triple, you can also proceed. So the we have seen the illustration of the design with one example, and that was the last equipment as far as heat transfer equipment is concerned. Okay, so the as far as heat transfer equipments design we have considered in this particular course, that is for shell and tube heat exchanger using two different methods: condenser, reboiler, and then evaporator. So all that are that heat transfer equipment. And today we will start the design of mass transfer equipment, which are um, commonly used in chemical industry. Okay, so the first one is the distillation column. Okay, that is an integral part of refinery or other chemical processes. Okay, but mostly it is used in refinery at multiple stages. Okay, so that you can see this that image, it is also the related to a refinery, and distillation column is a part of that. Okay, so we will discuss the that distillation column design at different stages. And some of that you have already read, but that we will not consider in detail, only glimpses we will consider over here just as a revision. And then we will proceed towards that design of distillation column considering new approach. Okay, so whatever you have read, just based on that we will develop. Okay, so let's discuss that distillation column. And like this image I have put to it will be clear that how why I have put that, because we need to move along like we need to track a long height. Okay, as far as this distillation column is concerned, with this we will start from the basics. Okay, so distillation and continuous process that we will discuss, and here we will revise mm, the concept which you have already aware of, okay, which you already know. Okay, so we will start from the basics which you have already read, I think, in mass transfer course. So that we will start from there only, but only summary we will cover over here. Then we will discuss continuous distillation, the basic principles. So what are the governing equation, how those governing equations are considered, all that we will consider over here, and that too in a what we can say brief way, not in very detailed way, because assuming that you know all these already. Okay, next is design of multi-component system. Okay, so as I have told you that some part of the design you have already covered. So design of like the binary system probably. Okay, design means that to find out the number of trays only. I think that much only you have completed. So that you have done, and based on that we will discuss the design of multi-component system. Okay, because when you consider any chemical process, refinery and all, you will not find a process where only binary system is being separated. Okay, binary component mixture is there, you have multiple component system. Okay, so how to proceed for design of that multi-component system? Design means to find out the number of trays. Okay. Other parameters you can decide uh, based on the complete design which we are going to discuss over here. But the number of trays for multi-component system we will start from there. Okay. So that would be new to you. And next. To that we will consider, once I'm having the multiple once I'm having the number of trays for multiple component system, we will proceed towards design, towards the plate efficiency calculations. And you also already have heard about, or you already aware of that, the plate efficiency, you must have read about Murphy plate efficiency. So that is the very basic definition. Okay. um, However, when we go for the actual plate efficiency, we need to consider that how much mass transfer is occurring, how much that geometry is contributing towards that efficiency. So all that parameters, all that factor we will count over here. So obviously that plate efficiency which we are going to discuss, the calculation part of that, that you have not read so far. Okay, only basic you aware that how much efficient, how much separation you expect. Okay, but that separation is not like a complete parameter to decide the efficiency. You need to consider many more parameters. So all these parameters we will count over here. So that will be truly a new thing to you. And of course that will be based on whatever you aware, whatever you know already. Okay, so that is the plate efficiency. And finally we will consider the plate hydraulic design. Plate hydraulic design includes the design of a single plate. Okay, if I'm having the number of trays, how to consider design of a single tray, plate, and it depends on not only the separation, it depends on where it is available, like above feed, below feed, and what are the geometrical parameter we need to consider. Those all those parameter would be the part of this design. Okay, a design of a single plate. Okay, so based on that you can uh, complete the design of distillation column. That is, number of trays you have already calculated, plate efficiency you are already aware of, and then plate hydraulic single plate design you can do. And once you complete the single plate design, you will decide many more parameters apart from number of trays. Okay, and based on that you complete the design of distillation column only. Okay, so you can understand understand that we have started from the base and then we are moving upward towards design of single plate. Okay, in that way complete design of distillation column will be discussed, and uh, and that you will uh, y- through which you will get the um, what we can say, the knowledge to find out to complete the design of distillation column. Okay, but we need to start from the base. Okay, so we will start from the basic thing that you already have read in your mass transfer course. So from that only we will start. So now we will first of all revise the a few points about the distillation column. Okay, so that you can consider as a revision of your uh, concept. So distillation column, when I'm considering, that is the unit operation, and it is in this the whatever mixture is available in liquid form, that different components available in that, it is, these are separated using the thermal energy. Okay, so thermal energy we consider based on that what component is involved, that we have already designed, that is nothing but the reboiler. Okay, so you get the thermal energy, and that thermal energy will be required to achieve a required temperature, and at that temperature what constituent or what component can be separated, that depend on the constituents property or components property. Okay, so but that level we can achieve by providing heat, and that we consider, that we get from the reboiler. Okay, so that is the basic thing about this. Now how the separation occurs? Okay, that will depend on difference in vapor pressures. Okay, difference in vapor pressures, or more precisely we call as difference in volatility. Okay, so based on that we have the separation of different components. Okay, and the point is the difference in vapor pressure of different constituents at the same temperature, and through which we can get the separation. Okay, so this unit operation is also termed as a fractional distillation or fractionation, because complete feed is available as one component, or we can say as a one stream, and from that you get different components, so that we call as the fractionation. Okay, we fractionate the liquid stream. Okay, so liquid mixture which is to be separated into its components is fed to the column at one or more points along the stream, sorry, along the column. So you can consider feed as multiple feed inputs in distillation column, and in this way you can get the uh, that inlet streams. Okay, as we can consider multiple feed points. So when I'm considering this liquid mixture which is fed at multiple points along the length, so what happens, usually when we consider distillation, it is basically the two phases. Okay, liquid phase as well as vapor phase. So because of the density, liquid moves down, and uh, because of lighter density of the vapor, vapor moves up. Okay, so liquid follows the gravity, but vapor moves upward because of the density. Okay, in both density is involved, but obviously that will be more applicable to liquid. Okay, instead of vapor. So vapor moves up and liquid moves down. That is a natural movement of these streams. Vapor is produced by partial vaporization of liquid reaching the bottom of the column, and that partial vaporization we consider in reboiler. Okay, reboiler is used to generate the vapor which is continuously fed to the distillation column, and which moves upward. Okay, but in between vapor is not generated, vapor is only generated in the reboiler. Okay, So the remaining liquid which is withdrawn from the column as a bottom product rich in heavy component. Okay, so when we consider the reboiler, there you have seen that some part of that liquid is converted into vapor, and continuous discharge also we get from the reboiler. Okay, so that is nothing but the withdrawn of the bottom product, which is rich in heavy component. Okay, heavy and light, how you decide? Okay, based on volatility. Okay, so which is more volatile, that would be lighter. Okay, which is less volatile, that would be heavier. Okay, so vapor reaching the top of the column is partially or fully condensed. Okay, so I should not consider that the what is partial, what is total, that you understand. Okay, that we have already discussed in detail in condenser. Okay, so that you can refer. And part of the condensed liquid, which is we have the vapor from the top which enters into the condenser, and that converts into the liquid partially or fully, but the one part of that liquid is returning back to the distillation column, and that we call as a reflux. Okay, while the remaining is withdrawn as a distillate product. Okay, so in this way you can consider the liquid stream which is available in the distillation column. So liquid is because of the condensate, and vapor is because of the reboiler. Okay, liquid is without of because of the condenser. Okay, but whatever part of the liquid which is like returning back to the distillation column, apart from that, whatever stream is available after condensate, that we consider as a distillate, or the final, or the top product, right? Which is obviously rich in lighter component, not the heavier component. So like this you have different points about the distillate, about the distillation. And if you consider the continuous process of the distillation, the schematic you can see like this. And here I'm having number of trays. Okay, and as you can see, when I consider the tray will be available in this way, like one tray will be attached at this corner. Okay, another tray will attach at this corner. Actually, when I'm considering this distillation column, it is a cylindrical assembly. Okay, cylindrical vessel. Okay, so if you consider this plate, okay, it is not that it is only attached to this. Okay, it is attached to the inner periphery, whatever would be the cross section of the plate. Okay, because that plate is if you can understand this like if like this you can resemble with the baffle. Remember, baffle is attached to the inner periphery of the shell. Okay, in the similar line, this plate is attached to the inner periphery of the column. Okay, so here I'm having one plate. This is the second plate. This is third plate. Like that, I'm having plates depending upon different parameters, and those parameters could be plate spacing. Like here, you place one plate, and apart and uh, second plate you can place at certain distance, and that distance you can consider as the plate spacing. Okay, that you will decide in design. Okay, now if you consider a single plate, uh, not the complete diameter can be considered as a diameter of the plate. Okay, as you consider the baffle, certain part of that baffle we consider as a cut. Okay, so that also you will see over here. Okay, and this will decide that how much this distance should be. Okay, and this distance means this distance, or we can say this distance, which we call as the downcomer section. Okay, downcomer section means the open part of the plate, which is used to ensure that liquid movement should be smooth. Okay, because if you consider the reflux, it enters from the it basically uh, enters to the first plate. Okay, and then it when liquid comes over here, it travels the whole plate, or we can say the covered the whole plate, uh, or more precisely, it spreads over the plate. Okay, and the bottom which I'm considering, the liquid which is the vapor, sorry, the vapor which is coming from the bottom, it basically passes through these holes which are made over the plate, and vapor is passed through this hole, and liquid moves towards liquid will be available at the surface of the plate. Okay, and as vapor moves upward, it crosses the liquid which is available over the plate, and because of this cross, the mass transfer occurs, and constituent transfer from like liquid phase to vapor. Okay, because whatever vapor is available, that is enriched in what we can say, the lighter component. Okay, so the point is, when vapor moves upward and it interacts with the liquid, mass transfer occurs over here. Okay, and after that, whatever liquid is available, it moves down. If you see this particular part, okay, this particular section or this particular section, it decides that how much volume of the liquid will be available over the plate. Okay, once the liquid crosses this height, this then only it will come to downcomer. Okay, and once it is falling in downcomer, you can see this assembly. Okay, and this assembly also, everywhere this same assembly you will find, and this we call as downcomer apron. Okay, this we call as downcomer apron. So whatever liquid is available over the plate, once it crosses this particular section, and this we call as the weir height. Okay, this we call as the weir, and the that assembly above to this we call as the weir height. So once the liquid crosses the weir height, then only it comes down. Okay, it comes down, and this apron stops the liquid movement towards this. Okay, just it follows that path, and then it strikes or it falls to the stream which is available at the bottom. Okay, and if you can see that holes are not available in this particular section, or in this particular section, or in this particular section, so you, what is the point to consider this, like wherever the liquid falling from top plate to the bottom plate or to the lower plate, it will first stay over this section where the holes are not available, so there is no possibility to liquid to move down. Okay, obviously, because no hole is there, so liquid is stay over here, and then it will move in this direction. There is no other way for liquid to move. Okay, so liquid will move over the plate, and then again the vapor which is coming from the bottom, it crosses the liquid, and there we have the mass transfer activity. Okay, so the point is that liquid is not moving down in between. Okay, liquid has to follow a certain path, like it enters from here, it covers the whole plate. Okay, then it moves down from the from this downcomer, moves down, and here I am having the accumulation of the liquid, and then it further spreads over this plate, and then moves down. Okay, so that is a usual pattern of the liquid. Okay, uh, uh, we need to ensure that liquid should not move down from these holes, because these holes are simple holes. Okay, the holes does not know that it has to pass only the vapor and does not allow liquid to move down, because when liquid will be available over there, there are possibility to move down from these holes, but as liquid moves down from these holes through these holes, uh, what will happen, it will stop the movement of vapor through these holes. I hope you are getting my point. Only one thing can occur, either liquid will move or vapor will move through this hole, so we do not allow liquid to move down. And because of that, to ensure that, we need to consider the vapor flow in such a way so that it always keeps liquid over the plate and does not allow liquid to move down. And once the liquid move down from these holes, we call that as weeping condition. Okay, as weeping condition. So that is also a part of the design, that weeping should be avoided. Okay, so that we consider, that we will see in design how to avoid that condition. So that is the weeping. And feed is there, and you can see here I'm having two different section. One is rectification or enrichment section, second is stripping section. So what will happen in stripping section? In stripping section, the liquid which is sorry, the component which is available rich amount in liquid, that will be transferred to the vapor. Okay, so here constituents are transferring from liquid phase to gas phase or vapor phase. Okay, and therefore it is called stripping or adsorption. Fine. That we consider from liquid phase to the gas phase. Okay, actually it is not adsorption, it is deabsorption. Okay, absorption, you understand, that is from gas phase to liquid. Gas phase, we can say the liquid phase, and reverse of that would be deabsorption. Okay, on that we also call as stripping. Okay, because in this case the component which are available in liquid, in what we can say light components, that would be transferred to the vapor. Okay, and as vapor moves upward, it again takes the same lighter component from liquid to vapor. But this is not called as stripping section, this is called that rectification section or enrichment section. The reason being, here the liquid here the component is transferred is take sorry here the component is transferred from liquid to uh, vapor. Okay, so that it means in vapor already that component is available, okay, till it enters into the rectification section. Okay, so in that way we call that this section would be stripping section. Okay, however here whatever component is available in the vapor phase, that got enriched, okay, in concentration, therefore we call that as enrichment section. However, the component transfer will occur from that what we can say the that from liquid phase to vapor phase. Okay, so that is the thing. And uh, further, that component concentration increases in enrichment section or rectification section in vapor. Okay, depending upon the light component. Okay, and then it will exit the top of the column and then enters into the condensate. So in that way you can have uh, vapor has more lighter component, and the heavier component will be available with the liquid only. Okay, so therefore we consider lighter component from the top and heavy component from the bottom. Okay, so in this way you can consider the distillation procedure, distillation operation. And many points we have covered already, but many more we will cover in subsequent slides. Okay, so that is basically the, and what we can say, the continuous process. Okay, now when we consider this particular part, okay, when the liquid is coming down and over this section, the what we can say, the uh, holes are not available. It means it is this section is basically made to hold the liquid. Okay, and therefore we call that as calming zone. Okay, this particular section or this particular section where holes are not available, okay, around the periphery also, because that section we need to attach with the what we can say, with the inner periphery, so that so their holes are not possible to make. Okay, so wherever that part is there where holes are not available, we call that as calming zone. Okay, all that part we will discuss in detailed design also. Just 1 minute, please. So that is the details of distillation column which we have discussed, and much more we need to discuss about this. Okay, so where the top product is required as vapor, only sufficient liquid is condensed to provide the reflux flow to the column, and the condenser is referred to as partial condenser. So actually, that part we have already discussed in condenser design, when we call that as partial condenser or when we call that as total condenser. Okay, so that you already know. So this is the same point when we, sorry. Only you need to keep in mind that in what phase distillate you are getting. Okay, if it is in vapor phase, the partial condenser. If it is in liquid phase, that is total condenser. Condensation will occur. Okay, now when we consider the virtually pure top and bottom products. Okay, when we consider that it is in pure form, we can say possible to separate when I'm having binary system. Okay, when I'm having two components, then also little bit mixing is possible, but in that case at least we can get the pure component. Okay, uh, however, when I'm having more than two components, only single pure component can be produced either from top or bottom of the column. Okay, but if I'm having more than two components, it may not be possible that from any way you may have that two like you may have a pure component, that may be a little bit mixture is there, mixture is possible. So in that case, instead of single distillation column, we work with multiple distillation columns. Okay, so here we will discuss some of the basic equation, some of the basic principles about the continuous distillation. And the stage equation, when we consider this, if this schematic you see here, I'm having n is the nth tray we are, or nth stage we are considering, where fn is the feed at zn constant, zn fraction. Okay, and sn is the exit stream. Okay, you are taking product from there also at xn concentration or xn fraction. Here I'm having Vn plus 1 plus Vn plus 1 or Yn plus 1. Okay. And Vn Yn. That is vapor entering from vapor exiting the bottom tray, and this is vapor exiting from uh, that present tray. Okay, similarly here I'm having L uh, n minus 1 at x n minus 1. So L is basically liquid flow which is exiting the upper plate and coming down to the present plate. Okay, and ln is the exit from the present plate. Okay, and qn is the heat which I am providing. So the point is, when I'm considering this particular schematic, all possibility we have considered. All possibility means we are entering the feed, exiting the product, inlet of the like inlet and outlet streams that will there, and heat requirement also. If uh, all all combinations you can find over here, right? Okay, now the point is like, what about this nomenclature? How you have you can understand that nomenclature? That the easiest way is you can identify from where. Okay, please listen it carefully. From where or from which tray the stream is exiting. Okay, nomenclature is based on that tray. Okay, from which stream is exiting, not entering. Fine. So let's say if this Vn plus 1 I am considering, so it is exiting n plus 1th tray. Okay, similarly this is exiting nth tray, and this is exiting n minus 1th tray, and this is exiting nth tray. Okay, so as far as flow rates of vapor or liquid is concerned, and the respective nomenclature, that nomenclature will depend on the stream or depend on the stage or plate they are exiting, right? So in this way you can consider. Now we will make the material and energy balance. So if you see, that is when I'm considering material energy balance, it means we need to prepare, we need to put the envelope. So if I put the envelope around it, okay, like this, everywhere, like where I need to make the material and energy balance, first of all you should create the envelope for an envelope, and then in that envelope whatever streams are exiting or entering, that you need to consider. Okay, so if I put the envelope around this table, so what are the streams which are entering into it? Okay, like this stream is entering, this is entering, and this stream is entering. Exiting this one, and this one. Okay, so in that way, you can consider streams which are entering and which are exiting, and just make the balance. Okay, and that basically we are considering that balance based on component. Okay, so y n plus 1 into v n plus 1. Similarly, that l n minus 1, x n minus 1, y and x, I don't need to differentiate, or I don't need to describe. You already know that, right? Why we consider when we are considering fraction, that fraction in vapor phase, and x will be considered fraction in liquid phase. Okay, Zn is the fraction of freed. So all this and these streams are entering, these streams are exiting. So simple, you need to make the component balance. Okay. And this is all the revision. I believe that you know already all this. Okay. You have read all this. Okay. But we will develop from here. Okay. Energy balance, when I'm telling energy balance, would be your whatever vapor is considering, with that enthalpy of vapor will be involved, and whatever liquid is considering, that enthalpy of liquid will be involved with it. Okay, along with whether we are like supplying the heat on that plate or removing the heat from that plate. Okay, so that you can consider. So again, the envelope we will draw, and that envelope, the inlet should be this, and this. Okay, four inlets are there with respective enthalpies, and three exits. This one, and this one. Okay, so wherever I'm having the vapor, there I will consider capital H enthalpy of vapor, and wherever I'm having the liquid, we will consider enthalpy of liquid, small h. Okay, like that, like feed is in liquid, so that should be hf. Like that, you can consider the material energy balance. Okay, and for equilibrium, we used to consider this, that equilibrium of vapor fraction to vapor vapor fraction, component in vapor fraction to component in liquid fraction, that would be related with the equivalent, that equilibrium constant. Okay. Now, next part is the design of multi-component system. You please keep on seeing that as we have decided the content in the beginning to reach the top, in the same line, uh, d- I'm just continuing this discussion. Okay, so design of multi-component system we will consider over here, and design of binary system you already know. And for that binary system, the number of trays you can calculate based on McCabe-Thiele method. Okay, so that you have already done. Right. So when we consider multi-component system, the problem of determining the stage and reflux requirement for multi-component distillation is much more complicated in comparison to binary system, and that you understand also. Okay, when the feed contains more than two components, it is not possible to specify the complete composition of top and bottom products independently. Okay, so in that way you will obtain the mixture, but of course the a few components you can separate, um, almost completely you can separate. Okay, like if we have multi-component system, the lightest and heaviest. Okay, so but obviously complete specification to to define top and bottom composition, that is difficult with multi-component system. Okay, therefore what we do over here, the separation of top and bottom product is specified by setting limits on two key components between which it is desired to make the separation. Actually, what happens when we consider this uh, multi-component system? Okay, it is difficult to specify the composition of top and bottom for all products. Okay, therefore what we do, we usually consider from multi-component system, we basically define key components. Okay, key components means uh, the major components between which separation is desirable. Okay, if I'm having binary system, uh, there is no need, because one would be lighter, one would be heavier, so separation is possible. But here, when I'm having multi-component system, we basically consider key component in what respect? Key component in volatility respect. Like one we define as the light key, another we define as the heavy key, and we consider separation between these two. Okay, I hope you are getting my point. So in multi-component system, we basically define the key components, and separation we consider between these two components only. Above that, whatever component are available, okay, that would be that will would be collected with distillate, and other the heavier component beyond the heavy key, that would be collected as bottom product. I hope uh, please try and understand, it is new to you, but when we see the detailed procedure and all, I hope it will be clear to you what I'm trying to emphasize on. Okay, but the first step is, in multi-component system we need to define key components. Okay, and these key components are only two, not more than that. Okay, only two key components we define, between which we basically separate. We considered the separation. Okay, so the first step is to define key component. So let's see how to define that key component. Okay, and when we consider key component, those key component are called as light and heavy key component, right? That we call as light and heavy key components. uh Let me, okay, instead of reading all this, let me discuss with this table. uh, let's say if I'm having four different components A, B, C, D. Okay, you need to arrange all these components in decreasing volatility. Number one, okay, decreasing volatility, that you understand, the most volatile should be at top and least volatile should be at bottom. Okay, now this is the feed, and we define the top and bottom product. So how we will define this light and heavy key component? Okay, light and heavy key component can be defined as, let's discuss first the light key. Okay, so light key should be the lightest in bottom. Okay, we have feed, we have top and bottom. Okay, this specification we can we already have, right? For to decide any distillation column, sorry, to decide any separation, we basically uh, first of all figure out that this component we get at the top and this at the bottom, so that is already available to us. Now the light key should be the lightest in bottom. It is reverse. Okay, light key component means lightest in bottom. It means uh, lighter component, we usually see lighter component, we usually see lighter components at top, okay, not at the bottom. But here, to define the light key, we usually we consider this definition that uh, lightest component available in bottom. Please consider that this is reverse. Okay, from that you need to keep in mind lightest in bottom is the light key. Lightest in bottom, if you see here, I'm having B, C, D. A is not available because A is the lightest, so that will go at the top. Okay, but the lightest component available to us is B, because this table I made uh, to arrange the component in decreasing volatility. So whatever is available at as first component in bottom, that would be lightest in bottom. Okay, so definition wise, lightest in bottom is the light key, right? Similarly, heaviest in top is the heavy key. Okay, please keep in mind, lightest in bottom is the light key, heaviest in top is the heavy key, because usually heavy key heavy component where we obtain that is at the bottom, but this is reverse. Okay, lightest in uh, bottom and heaviest in top. Okay, so in this way you can define B is your light key and C is your heavy key, and you need to design the system in such a way so that separation between B and C is possible. Okay, so once I'm having separation between B and C, A and B you will get at the top, and C and D you will get at the bottom. And further, because it would be binary system, the separation can occur by uh, putting putting another distillation column, right? So in this way, the basic step is to define the key components, and key components are two in number. One is light, one is heavy, and lightest in bottom is the light key, heaviest in top is the heavy key. Okay, I hope you are getting this. So based on that, if we decide the light key and heavy key component, please, if you have any confusion, please discuss. I understand this is new to you. Okay, so uh, in this way you can define the light and heavy key. And another point is, what is this D and what is this A? B and C you can understand, that is, B is the light key, C is the heavy key. What about this A and D? Okay, A is light non-key. Okay, because it is at the top, so obviously it is lighter, but that should be light non-key, because light key is this. So this is light non-key, right? Similarly, this D is the heavy non-key. Heavy key is C. Okay, and below that, whatever would be the components are available, that would that will be considered as heavy non-keys. Okay, and above B, whatever component will be available, that would be a light non-keys. Right? So in this way, you can consider. Just give me 1 minute. Okay. So I hope you have understood what is light key and what is heavy key, and we will proceed further. Now, to find out the number of trays for multi-component system, okay, to find out number of trays for multi-component system, we have one specific method, and that we call as Henstebeck's method. Okay, you have not studied that before. That probably before you have only read McCabe-Thiele method. Okay, so here I'm having this method for multi-component system, and that is Henstebeck's method. First of all, I will discuss about the uh, what this procedure, what this method consider, and then we will proceed. Okay. Okay. So this approach based works on a few assumptions. Okay, the assumption is like for any component I, the material balance equation and equilibrium relationship can be written in terms of individual component molar flow rate in place of component composition. Okay. Uh, the main concern over here is we need to whatever the separation is required, based on that we define the light key and heavy key, and above light key is light non key and below heavy key are that is heavy non keys. Okay, it means the components are independent now, right? Components are independent, and the uh, so in that way we define the we consider each component as a separate stream, each component as a separate stream. Okay, therefore we consider individual component molar flow rate in place of component composition. Okay, let's say if you are having this, we are considering for rectifying section. Usually the balance we have is Vn plus 1 should be equal to Ln plus D. Okay, Vn plus 1, that is, this is the inlet, and exit is this ln, and exit is this d. Okay, that is, we are making the balance in enrichment section. Okay, this equation you are familiar with. Okay, nothing new. Okay, but the proceed how to consider that, that is new. Okay, so if I usually we consider in this way. Okay, so this Vn plus 1 and this Ln and this D, these are what? These are total flow rates of vapor, liquid, and distillate. Okay, Henstebeck's method says, just 1 minute, please. Okay, okay. So this equation you are already familiar with, but Henstebeck says this is also the equilibrium relation, right? That you know. The Henstebeck method says that instead of total flow rate, we will consider component molar flow rate. Like this is for ith component and its flow Vn plus 1 I, that should be equal to ln I plus di. Okay, it means that we are representing that with the small letters. Okay, not the capital letter. Capital letter shows the total flow rate, and small letter shows what we can say, the component individual flow rate. Okay, so ये Vn plus 1 I ith component, uh, the molar flow in this stream. Okay, similarly lni plus di, this is only for the sake of having different components, okay, to see different components individually. Okay, similarly, this yi should be VNI by capital V. Okay, that is only this fraction is, right? So that VNI, that is equal to KNI, and this V will be available over here, so that we have taken over here V by L, Ni. Okay, so this would be X, and this divided by this V should be Y. Okay, you understand that? Okay, so this is the assumption by based on which Henstebeck's method works, and this is for the rectification section. For stripping section, you see, this is the schematic where this ln plus 1, that should be equal to Vn plus B. Okay, this is the usual balance we make, and this is, you see, this is a small uh, L is small v small b, so that is nothing but in the individual component molar flow. Okay, so this is these equations are for rectifying section, and we have the nomenclature like LNI is the liquid flow rate of ith component from stage n, like that you can consider. Okay, subscript prime we usually consider to define the equation in is stripping section. Okay, that you know already. Capital V and L are total flow rates. Okay, that we have already discussed. So the Henstebeck's method consider all component individually. That you need to keep in mind. Okay, now once we define the flow, once we represent each component with respective flow, we will proceed towards like the in further step. uh, Let me tell you in this way, as we have defined flow rates of each component, right? Among these component, one is light, one is heavy, as we have defined earlier. Okay, so obviously light and heavy key component should also have the flow rate. Okay, so the consideration over here is the all light non keys. Sorry. Hello. Okay, so the point is all non light key component we can define based on the molar flow rate of individual components. So all those flow rates would be added. Just try and understand. Okay, uh, you have defined the individual component flow rates, right? And whatever light non-key components are there, you will add flow rates of those components. That is one thing. Another thing is, whatever non-heavy key components are available, you will add flow rates of all those components, light keys, all, sorry, non-light key and non-heavy keys component. Okay, so these are two things. It means all non-component you have collected together, right? In light section also, in heavy section also. Okay, you already know the total flow rate, capital L capital V, that is usually given in the distillation problem. Okay, so that total flow rate you already know. From that total flow rate, if you deduct the summation of flow rates of non keys, okay, what flow rate you will have, or you will remain with? You will remain with the flow rate of only key components, right? Just see the language and then you will understand. But the thing is, uh, you need to collect all non-key component in light section together, and all non-key component in heavy section together. Okay, deduct this combined flow from the total flow of vapor as well as liquid, you will find the flow of key components only. Okay, so to reduce the multi-component system to equivalent binary system, it is necessary to estimate the flow rate of key components throughout the column. Okay, so Henstebeck makes use of the fact that in a typical distillation column, the flow rates of each of light non-key, okay, each of light non-key components approach a constant or limiting rate. That you is another assumption you take, that all non-key, either in light section or heavy section, all the components in these regions, uh, it will give the constant flow, or that we call as the limiting rate. Okay, so you see the in a typical distillation, the flow rates of each of light non-key component approach a constant. Okay, similarly in rectifying section, uh, sorry, this is limiting rate of constant flow of light key in rectifying section. Okay, the flow of each heavy non-key component approach limiting flow rate in stripping section. Okay, so in this way you can consider rectifying section and stripping section, and all non-key components whatever is available, you combine them, and then that we consider as a constant, that those component will not vary the flow, right? And then putting the flow rates of non-key equal to these limiting rates in each section enables the combined flows of key component to be estimated. So the point is, first of all, what we have done, we have represented all component with their respective molar flow. Fine. Second is, whatever non-keys are available, their flow rates, or their flow we consider as constant. Okay, and how to find this limiting rate and all that we will discuss. Okay, so once I define the constant flow or limiting flow of non-key component, that we deduct from the total flow, and then we get the flow of combined keys only. Okay, combined keys means light key and heavy key only. Okay, so once I deduct the non-key flow rates from total, what exactly I am doing? I am just representing the multiple component problem into binary problem. Okay, so therefore this method, Henstebeck's method, is also called as pseudo-binary method. Okay, or pseudo binary approach, because exactly binary is not there, but we are making from multi component to binary system. And once you make the binary system, you have only two components to deal with, and then you will apply McCabe-Thiele method to find number of trays. Okay, what through that, what you are considering, you are considering that separation is occurring between key components only. One is light, another is heavy. I hope you are getting my point. Okay, if some confusion is there, please discuss. Okay, so so the next step is how to find the limiting flow rates of non-key. Okay, before that you need to identify what are the light and what are the heavy key, and so that you can get what are the light non-keys and what are the non-heavy keys, heavy non-keys. Okay, so further we need to find out the uh, expression for this Henstebeck method in stripping section. Sorry, in rectifying section, we consider LE and VE as the flow of combined keys. Okay, and capital L, capital V, you know the total flow rate of that liquid and vapor, and from this we will deduct summation Li underscore and summation Vi underscore. These are the limiting flow rates of non-keys. Okay, so from total, if you deduct the summation of all non-key flow rates, you will have the flow rates of key components only. So this is for rectifying section, for this is for stripping section. Okay, where LE and VE are estimated flow rates of combined key like this. Li and Vi, that is Li and Vi, are limiting liquid and vapor flow rates of non-key components lighter than the keys in available in rectifying section. So these are lighter than the light key. Okay. Similarly, Li prime and Vr prime are the limiting liquid and vapor rates of non-key components heavier than the heavy key in stripping section. Heavier than the keys in stripping section. So this key would be nothing but the heavy key, and this key would be nothing but the light key, right? Now we will find out the flow rates of that limiting flow rates of non-key components. These are some expression which are given. Li underscore that should be di by alpha I minus 1. Alpha A is the relative volatility of ith component with respect to heavy key. Okay, all relative volatility over here will be with respect to heavy key. Okay. Similarly, here I'm having Vi, that should be Li underscore plus Di. Please make the correction over here. That should be underscore. Similarly, this should be underscore. Okay. So in this way, you can consider the limiting flow rates of non-key components. So that is alpha I and alpha Lk. That is the relative volatility of light key with respect to heavy key. Okay. So once you define the limiting flow rates, you can define the flow rate of key component, converting the problem into binary and then apply McCabe-Thiele method. Okay. So estimating the flow rates of combined key enable operating line to be drawn for equivalent binary system. So equilibrium line that you can draw to follow this, considering different value of x, you can have different value of y. Alpha Lk, light relative volatility of light key with respect to heavy key, and these x and y will be referred to that vapor and liquid concentration of light key. Okay, the component in vapor and liquid, and that component should be light key only. Now we will see one example to find out the find out the number of uh, trays. Okay, and the example is like this. Example I have directly taken from volume 6. Okay, Richardson Coulson volume 6 chapter 11. Okay, so that this example you can find there as well. And I would like to tell that if you have fourth edition of volume 6, okay, fourth edition of volume 6, in that Henstebeck's method is given. Okay, I think it is also given in fifth edition, but not recent edition. Sixth, seventh, if you have, it does not have that Henstebeck's method. That is correctly, I remember for fourth edition, but maybe it is in fifth or so. But below four, all in all edition, that method is available. Okay, so that you can see. So we need to estimate the number of ideal trays needed in butane pentane splitter defined by the composition given in the table below, with which I'll show. The column will operate at the pressure of 8.3 bar with the reflux ratio of 2.5. The feed is at boiling point. So if you see here, I'm having 5 different components. Feed is available like this. Top is 45 and bottom is 55 kilomole. Feed is 100. Okay, so you can first is this is the reflux ratio, right? 2.5. Okay, and feed is available at boiling point. So if you consider Q of that, so Q should be 0. Remember, there are depending upon the feed condition, we have Q line. Okay, so that you can see depending upon the boiling point. Okay. So here I'm having 5 different components. So we need to first figure out what is light key and heavy key. So I think you can choose very clearly that light, by definition, please proceed. uh, by definition it says that lightest in bottom is this one. Okay, don't uh, consider that based on the value available over here, whether if it is one and you can say that it is lesser, that is not the thing. That can be more even. Okay, so the but of course it would be lesser, but it is not always it is least. That may be equal or that may be less. Both, in both way it occurs, and that in some way that may be greater also, but that is I think rare. Okay, so the lightest in top, sorry, lightest in bottom. So how we consider these are lightest, because we consider that this table is arranged in decreasing volatility, then only it can be said, it can be told. Okay, so we need to arrange all component in decreasing volatility, and then we consider that lightest in top, lightest in bottom. Lightest in bottom is the light key and heaviest in top is the heavy key. So C4, NC4 is the light key, NC5 is the heavy key. And what about this sorry, NC4 is the light key, IC5 is the heavy key. And this NC5 is heavy, not non-key. And similarly, C3, IC4, these are light non-keys, right? So we can figure out this as light key and this as heavy key. Average volatility we can find, and that should be at top and bottom temperature, so we need to consider at average temperature, so that you can find out like this. Now we will find out calculation of non-key flows. Okay, so this non-key, light non-key, these are available. This is heavy non-key, and alpha I, di, all these values are given already. Where it is given? In this table. Okay, in this table it is, these values are already given, and alpha is available over here. This one you need to count. Okay, so alpha I, di, for all these that you can see, now you can find out li underscore and vi underscore, and so you can find out summation of these two and summation of these two. This is simple based on expression only. Okay, no complication uh, is here, but but you need to understand the method properly. Okay, vi prime, li prime, you can see over here like this. And once I'm having all these values, we can deduct that from total flow to find out flow of combined keys. Okay, so you can see here flows of combined key when I'm considering, that is le, that is l minus summation li underscore. Summation li underscore is this. Okay, this should be l, and l should be your l by d is r, so l should be dr. R is the reflux ratio 2.5, and d is total distillate value. Remember, that is 45. It is given already like this, and 2.5 is the reflux ratio. So you can consider this and calculate LE. VE should be that VE, how you will consider VE should be L plus D. Okay, L plus D, that you can consider like this. VE should be this because it is at the feed is at boiling point, and LE prime when I'm considering that should be VE plus B. Okay, just we already made the balance. Okay, VE here you see in the rectifying section V plus B. So this is V, which is already available over here. B is the bottom. Okay, so based on that you can find out LE VE and LE prime VE prime. And once I'm having this flow rate of combined keys, we can find out slope of operating line in rectification section and operating and stripping section. From here onward you need to follow the McCabe-Thiele method. Okay, slope of top and bottom operating line, that you know already, that you have read in your mass transfer course. Okay, this is the equilibrium correlation which we have just discussed. uh, and for different x we can have different y, so we can draw the McCabe-Thiele diagram as you can see over here, and this is the 45-degree line. Okay, and this is a slope of light key, slope of rectifying section and stripping section that you can draw. Okay, and you can follow this McCabe-Thiele method. There is, I'm not going to discuss that. Only XD, XF, and XB, how you can consider. If you see XB is for bottom, and that too we will define based on light and heavy key. Here, from here onward, we consider that separation will be done only with in the key components. Okay, so XB should be flow of light key by flow of light key and heavy key. Okay, so that you can consider over here. Like XB, you can consider this is for this is for light key and this is for heavy key. So 1 by 20. Okay, XB. XD should be 24 by 25, right? This is 24 by 25. XF should be 25 by 45, right? So in this way, you can consider the uh, these dots. Okay, XD, XF, and XB, and then you can that uh, make the steps to find out the number of trays. So in this way you can from here you can follow the McCabe-Thiele method, and in this way you can do the multi-component system design or system multi-component system number of trays. And this is only between light key and heavy key. So above light key, whatever components are going at the top, further distillation will be required for those components. If it is more than two, you need to consider a multi-component system approach there itself. Okay, there also. And similarly for bottom, if it is only two component binary, direct McCabe-Thiele method you can apply. So in this way, multi-component system separation is possible with series of distillation column, not with single column. Okay, right. So in this way, you can find out uh, the number of trays for multi-component system using MCAP, using Henstedt method, and that is basically based on graphical approach, because final number of trays you are finding through this uh, by stepping in this graph, by making steps in this graph only. Okay, so that is the Henstedt method is based on this graphical approach. Okay, so here I'm stopping this lecture. We will discuss tomorrow from here onwards. Okay, so that's all for today. Thank you, everyone. And if you have any query, you please discuss. Okay, so that's all from my side if no query is there. So thank you, everyone, for your patience. Thank you.